Greetings, welcome to APchemistrycourse. Today's lesson I'm going to talk about the introduction to Vesper Theory, or also known as the Nh3 theory. It was awarded for those two chemists, and it was just known as the Gillespie and Nh3 theory, which talks about the two chemists, the Ronald Nh3 and Ronald Gillespie, who introduced the idea of Vesper in 1956. They said that there are 3D models of molecules and that we can see, and of course visualized, not seen like with the naked eye. And in that idea, it's based on that molecules have 3D shapes. They're not like in textbooks that we can't see them, like, or flat or something like that, but actually like we can see them and they're like 3D shaped. So let's talk about it right now. As I said, 1956, Ronald Gillespie introduced the idea of the Vesper theory, which stands for valence shell electron pair repulsion. Not only about the 3D models, but also about how electrons play a role on the model itself. Alright, so let's start. Right over here, let me erase that, that was an old model. Right over here, we can see 5 families right over here in the chart. Now, I'd like to call this the family chart, because it contains different families of the Vesper model. So let's start with the first one. The first one is called the 2-thing, 3-thing, then the second one, then 4th, and 5th, 6th things. What does that mean? Thing, I know it's not scientific, but to make it simple for you, it just stands for number of atoms and pair of electrons. The lone pair of electrons. So when I say things, it counts atoms and lone pair of electrons. Alright, so that's the meaning of the things. Another idea, before we start taking the first model, when we talk about the Vesper model, ionic compounds are not included in, unless if we have a polyatomic ion bond. So that's it. Alright, let's start talking about that first model. What does the 2 things mean? 2 things mean, in the first model, we have a central atom, and the first thing. Alright? So what is the first thing? As I said, it can be atoms or lone pair of electrons. You can see here we have only 2 things, 2 atoms. Now, though this model has 180 degrees. Why? If we look at it, we can see in a smaller, if we like look at it really good, we can see that the atom here, the dark atom, has electrons, and the light atom, the central one, has electrons. They're sharing them. They're like baskets giving each other what they have or what they contain. Here electrons, here electrons. Now they're sharing it. What's causing that model to be straight is the electrons. Those pairs of electrons that over here in the bond are not allowing the atoms to get closer to each other. They're rather pushing on each other, causing them to look straight. And that model is called the linear model. The linear model of the of any compound. So, as an example, we can take, for example, carbon dioxide, CO2. Carbon dioxide, Vesper, sorry, my bad. Carbon dioxide has a Vesper model of a linear, but it's like that. CO2 is simply C, then we have oxygen, we have here 2 oxygen. Alright, so we have first bond, that's single, and then we're going to have our second bond, sorry my bad, here. So we're going to have our second bond right over here. Then we have another bond right over here and another bond right over here. We can see that there is a double bond right over here. Oh wait, do number of bonds affect the molecule shape? Well, the answer for that, it's no. The rule states that number of bonds does not affect the shape of a compound, or the Vesper shape. So we can have a double bond or triple bond and the shape will still be a linear, 180 degrees. So that's the idea. Let's just understand the idea that first thing is first. Whenever we say things, they are the atoms that are bonded to the central atom. So no matter what, it either can be lone pair of electrons or can be atoms. They are related to the central atom. Central atom is never counted as a thing because it's the center of everything. Alright, second rule. Number of bonds does not affect the shape. We can have a double, triple, single, still in the same shape. And as we saw here, we have a double bond and a double bond, and still it's linear. Alright, as I said, 180 degrees. Alright. Now, it's actually really simple to memorize, but I wrote them down just so you can visualize them and just look at, have a small peek and understand what are their angles. Oh, we talked about the linear model. Now, of course, linear model is the only member of the first family member, which is the two-thing family member. All right. Next family, the three things. It consists of a central atom, does not count as a thing, and another atom bonded to it, another atom, and another atom. Remember, central atom is the center, does not count as a thing. We can see that we have 1, 2, 3 things that are just like what are here that are just bonded to the central atom. Now what we notice here is that there's a bond angle of 120 degrees. But what is that shape called? It's called a trigonal planar. So it's a trigonal planar, which looks like this. I modeled here a trigonal planar. As you can see, it looks like that one, exactly, right over here. We have a 120 degree between them, a bond angle of 120 degree. You can see it's called trigonal because we have 3 atoms around, and planar because if you look at it from that side, and looks like a sheet of paper. So it's plain like paper. Alright, so that's the trigonal planar. Alright. So that's the first family member, which consists of 3 things. What about the second family member? Do you expect it to have also 3 atoms bonded to it? Well, let's just see. Well, we have central atom, 1 atom bonded right over here, 1 atom bonded right over here. You would like to draw another one up there? Well, you're wrong, because we're going to draw this bubble-shaped thing, which is going to be the lone pair of electrons. What does that mean? In the previous example, the trigonal planar, we had, my bad, alright, so we had a atom bonded right over here. An example, if you look at it, is BH3. Boron, sorry, that will be not clear, so boron, here, H, oh my god, I'm just goofy. Alright, so my bad, it's going to be boron. So boron here, and it's going to have H, 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 single, single, single. You can see 1, 2, 3 atoms. They're bonded together. You can see that there's nothing above them. Do you see anything around the central atom? No. That means we just have atoms as things. But what about the other one that we just talked about? The one that has a bubble. What is a bubble? As you said, it's the lone pair of electrons. Let's talk about it. As an example for that, it's going to be tin chloride, SnCl2. If we draw it, it's going to be like this: Cn, 1, 2, 3, 4. I don't know what's up with that pen. Anyway, and Cl right over here, Cl right over there. We have a single, single. How many electrons do we see here? We see 1 and a 2. Does that make a pair? Yes, it does. So if we look at the model of SnCl2, the Cl is right over here, and the Sn is right over here. What about those? 1 and 1. Those make a pair, and they're going to be right over here. The 2E-. Those are the lone pair. What does it mean? It means after we have a bond, we have 2 electrons that are in the central atom that are not related to that bond. So what happens here, it affects the model in a way that it's surprising. because we know that there's a repulsion of electrons, of the valence electrons, the electrons of of tin are pushing on the chlorine atoms. They're pushing on them, so they're not letting them just go a little bit further away. They're pushing on them, so they want to repel. They're pushing each other, but there's also force pushing on them from here. So we have they want to go there, but there's a force also pushing right over here. So they're causing them to be bent. They're pressurized to be bent, and they're going to have a bond angle of approximately 116. That's the bond angle, as you can see, it's written right over here. They're really simple. You don't even have to memorize them. It's by logic. First one is 180 degree. You add another atom, there's going to be a little bit of force pushing downwards. So that will decrease it to 120. Then we go to the other one. We're going to have the lone pair of electrons, which is going to push more. So we're going to have 116. So it decreases approximately, of course. So that's how you can just predict them. But memorizing is a key point. But in that way you can understand that's always in decrease. So let's go to the last family member. Of course we have more for the other videos. That family member is going to be the 4 things. We have 1, 2, 3, 4. That looks weird, doesn't it? Indeed it does. But I just built one for you right over here. As you can see, we have 1, 2, 3, 4. We have the 1, 2, 3, and 4. That is called a tetrahedron. Of course, I forgot to mention that name, which is going to be called a bent. So that model right over here is going to be called bent model, and that one is going to be called a tetrahedron. Alright. So tetrahedral. Tetra for 4, hedral for the 4 atoms. So we want to have a tetrahedral. An example of that can be CH4, methane. So we have carbon, hydrogen, 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 hydrogen. Single, 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 single. You can see single, 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 single. That's a good example of a tetrahedron. As you can see, carbon atoms are over here, and the hydrogens are just around it. And the bond angle of such shape is going to be 109. So 109.5 degrees. So that's the bond angle that is going to be for a tetrahedral. 109.5 degrees, which is the bond angle of what? You're right. The bond angle of a tetrahedron. Alright, so let's take another example. Let's call it tetrahedron. Great. So another one is going to be something similar. 4 things. We have a central atom. We have one atom, or one thing, and one thing. 3 things. We're missing one more thing. Can you guess what is it? You're right. It would be 100% the lone pair of electrons. That looks weird. Is that called a tetrahedral? We have 4 things. Well, you can't say so. It's called a Trigonal Pyramidal. So it's called a Trigonal Pyramidal. You can see that it looks like a pyramid, and we have 3 things, and we have the lone pair of electrons pushing on it. You can imagine it like that. Without the upper atom, we have them like that. The electrons are pushing on this down. So on this shape, we're going to have the Trigonal Pyramidal, and it's going to have a bond angle. As you can see, it's not even written, but we can just memorize it. It's going to be 107 degrees. So we're going to have 107 degrees, the bond angle between the trigonal in the Trigonal Pyramidal. An example of that can be the Ammonia Nh3. Nitrogen, hydrogen, hydrogen, hydrogen. single, single, single. We have a single, single, single. What do you see above there? Here, right, we have a lone pair of electrons. And because of that, we're going to have them up there and pushing on that shape. Alright, so that's a trigonal pyramidal. Now let's take the last example. You are going to be surprised. So the last example is a central atom, an atom connected, an atom connected. Two things. It reminds you of band, right? But the band has one pair of electrons of the lone pair of electrons, one single pair. But here we're going to have two single pairs of lone electrons. Sorry, two pairs of lone electrons. So we're going to have more force pushing on that. So can you expect what the model looks like? You're right, it will look like bent, but although we have 1, 2, 3, 4 things around it, we have two lone pairs of electrons. Yeah, so they're pushing on them. We're going to have a bond angle of 105 degrees. Can you guess an example of such model? You're right, it's going to be water, H2O. Yes, water. We have oxygen. We're going to have 1, 2, 3, 4, 1 and 2. We're going to have hydrogen, single, single. I'm going to have one pair, two pairs, and they're going to be right over here at 105 degrees. And that's also called a bent. But the bent here is with two lone pairs of electrons. So that's all about the Vesper model, and I hope it was useful. Just let's understand everything, that we have two bent models. One of them has one lone pair of electrons and the other one has two lone pair of electrons. Alright, so this is all about our lesson for today, and I hope it was useful. See you in the next video.